Okay, so this is Thales' theorem, okay, el teorema de Thales, okay. So this, which I'm sure you've heard about in previous years, okay, but I guess you don't remember it that well. So let's review that. And this comes or this derives from the fact that we have similar figures, okay, from similarity, from the principle of similarity. So you know that we've been working with similar figures. You know that two similar figures are those which have the same shape but not the same size. Okay? They also have the same size. They are not only similar, but they are congruent. Okay? So in this case, if they are similar, they have the same shape but not the same size. So that means that they are proportional, okay, in all of their sides. So if I take, for instance, side A in this triangle and side A prime in this other triangle, and I divide them, the relationship, the ratio has to be the same as the ratio between B and B prime, okay, because they are proportional, okay. And this equation or this principle or this is what will give us the Thales theorem now, okay. So this is like if we place two similar triangles sharing one angle, we will have something like this. This is what we call two triangles in Thales position. Okay, so that is when two similar triangles are placed in such a way that they are sharing one angle and the opposite side is parallel. Okay, in both triangles. Okay. So from this we can go to Thales theorem, okay, which is made for like a more general case. Okay, this is what the theorem states. Segment AB divided by segment A prime B prime equals segment BC divided by segment B prime C prime. What does this mean? It means that, okay, you can see that this here we have two triangles, but if we get close enough, we can think of this as just lines, okay? If we turn this, actually I'm going to move to GeoGebra now because I think it's going to be more intuitive. But this is talking about the relationship between segments, okay? So here in GeoGebra, you can see, here it's easier to see a triangle, okay? There is a triangle here, AB prime. There is a second triangle, AC prime, okay? This smaller triangle is similar to the larger one, to the bigger one. Okay? They both are similar and they are in Thales position because they are sharing this angle and the opposite sides are parallel. And we also have the triangle ABB prime, which is also similar to the other two triangles because they are sharing this angle and the opposite sides are all parallel. Okay. So if we make a general statement for this theorem, it says the following. It states that if I have two transversals, okay, two transversals, two lines that, well, they could be parallel, but they don't have to, okay, in this case. So I have two transversals. And like if I get close enough, like it's no longer a triangle, but just lines. So if I have two transversals here, the blue lines, crossed by parallel lines, that's the key point. The red lines have to be parallel to each other. Okay. If I have two transversals crossed by some parallel lines, I can be sure that the relationship or the proportion between the segment BC and the segment B prime C prime is the same as the ratio or the proportion between CD and C prime D prime. Okay, and also is the same proportion as BD divided by D prime D prime. And it's also the same proportion as AB divided by AB prime, or AD divided by AB prime. Okay, so these proportions are all the same as long as I have two transversals crossed by parallel lines. That's the key point. The red lines have to be parallel. And I proved that here. Okay, distancia AB, distancia AB prima, that's this segment, the length of this segment, the measure of this segment, divided by the length of this segment. Okay, this divided by this is 1.12. BC divided by B prime D C prime, it's here, it's also 1.12. CD divided by C prime D prime, it's here, it's also 1.12. And AD divided by A B prime, it's also 1.12. Okay, if I move the point A, okay, those ratios change, but they are the same. Okay, they all change at the same time. So that's what Thales theorem states. Okay, and you see that if I keep moving this ratio keeps changing, but it's the same in all cases. Okay, and how do we express this? We express it like this. Okay, if I have two transversals crossed by some parallel lines, I can be sure that the proportion of the relation between AB and A prime B prime is the same as BC B prime C prime. It's the same as AC A prime C prime, and so on. Okay, those proportions hold. Okay. So let's solve one example from this recommended Excel. Okay, here my transversals, like as I said, well, this is for triangles, but it's actually the same. Okay? These two lines, this one, U, Y, U, V. Okay, so it's called in this direction. Okay, so Y, W, it's at, this is one line, this would be one line. Okay, this is a segment, but it will be one line. And then YV is another line. So those are my two transversals. Okay, and my two parallel lines would be V, W, and UX. Okay, it says here they are parallel. This is the symbol that represents that these two lines are parallel. Okay, so by Thales theorem, I can be sure that the relationship between these two segments is the same as the relation between this segment and this segment. And I'm missing this one, UB. Okay, so I can be sure that 8 over 6 equals 12, or well, I can do it in the other way, so it's easier. 6 over 8 equals UV over 12. Okay, I'm going to write it here. Okay, so 6 over 8, 6 over 8 equals UV over 12. Equals UV over 12. Okay, so this means that, okay, this 12 goes to the other side, multiplying. So I have that 6 times 12 divided by 8 equals UV. Okay, so let's calculate that. 6 times 12, okay, divided by 8, which is, so UV equals 9. Okay, and I can go here and I can say that UV equals 9. Okay. So I'm going to stop recording now.